Okay, we're going to review some game theory, and we're using this example of what I would call a saddle game. What we see here is the plot of the function x times y. So one of the coordinates is plotted here, and the other one is here. So we'll have a point somewhere in the space plane, and so for example this one here, this is the point -5, -5. That means x and y are both -5, and then the height of this is the value of f of xy, and this is x times y. So I don't know exactly where this goes up. I'll just try to plot something here. Now, what we also know is that for this point here, 0, 0, the function evaluates to 0. So 0 times 0 is 0, so there will be a point that is exactly on the saddle. All right. So for this function, if we would talk merely about optimization, let's say minimization, then there would be the possibility that x maybe stays at 1, and then y could go to -infinity, and then the function value would go to -infinity. So if we continue here, then which is outside of this graph, this could go arbitrarily small. At the same time, if we kind of move in this direction up here, then the function value can be arbitrarily big. But in game theory, we don't have two coordinates, kind of x and y, that are coordinated and that try to work together to achieve the global optimum or local optimum, but we have both coordinates are being controlled by two players that have different objectives. So when we look at the game, we could think of maybe a starting point here, and then one of the players controls this coordinate here. Let's just say this is x, and another player controls this coordinate here. Let's just say this is y. And the players are competing with each other. So we'll also say that one of the players will try to maximize. So we'll say that this player will try to achieve a score that's as high as possible, and this y player will try to minimize the function value. So y is the, let's call it minus or negative player, and x is the positive or the plus player. So if we're at this point, -5, -5, the function value will be -5 times -5 is 25. So in this case, the x player will be happier than the y player. While, of course, this is not the maximum that can be achieved, so the maximum is +infinity. In general, the x player is happy if the function value is positive, and the y player is happy if the function value is negative. That means at least they do better than their opponent. So now we are at this position -5, -5, and so each player can now think of where he would like the point to move, such that the player can improve his or her score. So the player can still only control its own coordinate. So the x player can try to move this point only along this direction. So the x direction is, you can move it either here or here. And let's think locally, where does the x player want to push the point to achieve a higher score? So the x player would like to move out further in this direction, because let's say it moves it to -6, then -6 times -5 would be 30, so then the score will be even larger than before, since 30 is bigger than 25. The Y player controls the y-axis, so the Y player can move either here, can move the point in this direction, or it can move the point in this direction. So where does the player want to move? The player wants to move in this direction. So, for example, Y could move the Y coordinate to -4, and then -4 times -5 is 20. So Y, while still the value is positive, it gets a bit smaller, and the Y player would be a bit happier than before. So in contrast to optimization, we basically have two objective values now, and typically we don't talk about the optima for this game theory setup, but we talk about equilibria. And so one thing to know is the concept of a Nash equilibrium. So, for example, for this game, the Nash equilibrium is at the point 0, 0. And the Nash equilibrium is a set of choices, so that is a point in this 2D domain, so that no player has anything to gain by changing only their own choice. So now the X player, the score is 0, so 0 times 0 is 0, can now think, how can I improve my score when I'm at this point? But locally, the player can't do anything, because changing to positive, let's say +5, the score is still 0, and changing to negative, -5, score would also be 0. And for the Y, the negative player, the same. Y wants to make the score negative, but there's no way to do so. Regardless of how the Y coordinate changes, the product of Y and X is always 0, because we start at this point 0, 0. So locally, Y has nothing that he or she can do to improve the score. That means for this saddle game, we have one Nash equilibrium, and this Nash equilibrium is at this point 0, 0, where the X player chooses 0 and the Y player chooses 0. All the other points are no Nash equilibria. Let's just look at one more point. Maybe let's look at this point here. That is X is -5 and Y is 5. Here the score is negative, so -5 times 5 is -25, and so the X player as well as the Y player have a preferred direction where they can move such that the score for them improves. The X player wants the score to be larger, so X would like to move in this direction, and again X can only control the X coordinate, and Y would like the score to be smaller, so Y would move in this direction. And again, no other points are Nash equilibria, only the 0, 0 point is a Nash equilibrium. So on this slide, we just see written down what we discussed before. And now let's ask the question, how can we find such an equilibrium? So the main algorithm we use in the context of deep learning are variations of alternating gradient descent. So we first ask player X, we are at one particular point in this game, where do you want to move? And player X would compute the gradient of that means the gradient of his own objective function with respect to the variable the player X can control. So looking at the objective function of player X, the objective function is X times Y. So the player wants this to be as large as possible, and then the variable that the player can control is X. So we compute the derivative, the partial derivative of that, and that is Y. That means the player X always moves in the y direction. Now, this cannot be confused with always moving in the positive y direction. So if y is positive, then the player x wants to change x to also be positive, to be more positive, and if y is negative, then player x wants x to move in the negative direction. Then player y would like the function to be negative as small as possible, so the objective of player y is minus xy, and then computing the partial derivative of minus xy with respect to the variable the player can control, y, we obtain minus x. Now again, this does not mean we always go negative, it just means that depending on what player x chooses, so for example, if x chose a positive value, so let's say x is 10, then y would like to go into the negative direction, make its own value smaller, and if x is negative, then the y player likes y to be bigger. So this is, again, this is quite simple, but not completely trivial. So it's important to think about this a bit more when first trying to do some game theory. So a great way to visualize this game is to actually do the following. For each point in the domain, we will ask the x player and the y player where they would like to move, and then we would obtain a vector. That is the combination of where both players are kind of pushing the current point. So the x player will give us the local direction of the x coordinate, the y player will give us the local direction of the y coordinate, and then for every point in the domain, we can plot this. So here we see the visualization. These lines here, this might be the isocontours of the actual saddle. So let's say the yellow values are the higher positive values and the blue are the negative values. And then the 0 point would be here. So this is the equilibrium of the game. So if you're at some point, let's say this point x here, and we ask the players, where do you want to go? Then together they would push us into this direction. Alright, let's say this is the x player controls this x coordinate here, and the y player controls this y coordinate here. Now, at this particular point here, we look at the partial derivatives. So as we saw in the previous slide, for the x player, the partial derivative is y. That means if we are somewhere here, then maybe the partial derivative, so we look at y, this would be 1. So that means x wants to take a step of size 1 in the positive direction, and if we would be up here, for example, then x would like to step twice as much, so it would like to step 2 in the x direction. So therefore this arrow here is about twice as long than the arrow down there in the x direction. Now the y player looks at minus x. So x here, for both these points, the one up here and the one here, x is very small and slightly negative. So therefore, the y player wants, in both cases, to move slightly in the positive direction. So x is slightly negative, so it's slightly in the positive direction, but not very much because x is already quite small. And that gives us these vectors that have little x component here. Now, once we move over, let's say we move here and we are at some point here, then for the x player, nothing much has changed. I mean, they would still say that, okay, y is maybe a bit more than 1, so we want to still move quite a bit into the positive x direction. But the y player changed its mind direction-wise, so when we are right here at this point, the y player would like to slightly move downwards, because x now switched from being negative when we were over here to being positive when we are here. So there's a switch in the y strategy from going slightly negative here. Okay, so when we would start the game with some initialization, so let's say we start the game here, and we'll just follow, maybe using this alternating update steps, then we would expect kind of to go in circles. And we would not really reach the equilibrium that is here, but we would actually circle around the equilibrium. So we would say that the players run around the equilibrium in an orbit. You can imagine that this thing is not numerically super stable, so a slight inaccuracy might lead, if you try to actually numerically do these steps, might kind of bring this out of control, so maybe you'll spiral towards infinity. But maybe one could also ask, how can we slightly modify this so that instead of running in orbits, this actually will more like spiral towards the equilibrium? Now, these are some theoretical studies of GANs that have been undertaken, but at this point in time, I would say it's not really entirely clear how much the theory and the praxis of GANs actually align. So there seems to be quite a significant gap between theory and practice. And a lot of this gap is due to a lot of the heuristics and that people add to GANs to improve the training. But there are some things that are really important and that kind of carry over to what happens in practice. So first, there will be two objective functions, one for the generator and one for the discriminator. So we cannot expect that kind of the objective will now smoothly or almost smoothly decrease as we saw before, but we'll have these two objective functions, and they can they compete with each other. So we would also expect that maybe they'll oscillate a lot more than what we see with the networks that we studied previously, such as image classification. Also, the training is a lot less stable. It's possible that undesirable things happen. For example, things could spiral out of control, or we also don't want that one player starts dominating the game. For example, we don't want the discriminator to completely dominate the game, and in this case then the generator might have a hard time learning anything. So what we get, at least a bit from the theory, is that the training dynamics of GANs are going to be a lot more difficult than the training dynamics of other networks. All right, so we'll introduce this concept of a normal form game. So an n-player normal form game consists of a finite set of players, and then we have a set of pure strategies. So each player I has this set Si that gives all the choices that a player can choose from. And then when we combine the choices of all the players, so this S1 is the set for the first player, and so on and so forth, and Sn is the set for the nth player, and taking everything together, then we have S, which is a pure strategy profile. And so S is the space where basically the state can be chosen from, and one particular point is the strategy profile. So we have one particular choice for player 1, it would be S1, so this is a small s, and one, so on and so forth, and then one choice for player n would be small sn. So this s would be a point somewhere in this state space S. All right, so what we also have is a payoff function that is different for each player. So each player has its own payoff function ui that takes one element small s in this state space big S and maps it to a payout which is an element of R. So it can be positive or negative. And a game is finite if S is finite. That means if the choices that the players can choose from are finite sets. So here we introduce the concept of a zero-sum game and a few other terms. So a two-player game is a game with two players, which we have when we study generative adversarial networks. And then there's the idea of a constant sum game, and a two-player normal form game is a constant sum game if there exists a constant C, such that for each strategy profile S, and now this state space is S1 cross S2, so for each strategy profile S in this state space, we have U1 of S plus U2 of S equals C. Generally, what we have is that C equals 0. So that means that for this constant sum game, let's say we have a constant sum games are often called zero-sum games just because the constant is kind of arbitrary. So let's use this term a zero-sum game. So that would mean that U1 is the negative of U2, U2 is the negative of U1. So we'll have one function and one of the players has a positive sign in front of this function and the other player has a negative sign in front of this function. Such as what we had before, one player was looking at x times y and the other player as minus x times y in the saddle game. So the saddle game is a zero-sum game. Zero-sum games represent situations of pure competition. That means one player's gain, all right, this is a bit, must come at the expense of the other player. So player X can only win something if player Y loses something. Or in this zero-sum game, the player X gains exactly as much as the player Y loses. And that's why there's pure competition. So what we know from GANs, GANs are generally two-player games, and GANs are typically infinite, and the GANs, when they start out, maybe one form might be a zero-sum game, but then with all the modifications, GANs are not strictly zero-sum games anymore. GANs are infinite because they can pick from usually the variables are real values, so there's an infinite amount of options. And the other thing is that there's this idea of the structure of this game is common knowledge, so that all players know the payoff functions. So we don't have anything with players not knowing exactly what other players think, or we don't have these type of restrictions of